Then as the next one is let's think about the reaction trees. Okay, so think about the reaction coordinate. In this case, A B molecules, think about, and S0 and S1 state is like this. As we studied, when the light is absorbed, right, due to the Franck-Condon principle, keeping the structure, the molecules are change into the excited state, and then due to the extra energy of the vibrational energy, it can oscillate the molecule, right? So in a sense, after light absorption, the molecules start oscillate, right? And in some cases, the energy level of S1 state could something like this. In this case, if the vibrational oscillation energy is high enough, it could escape toward this way, which means A, B distance is getting long, and finally, and A and B are dissociated. That's a dissociation reaction, and the chemical, the bond dissociation origin, right? And also, I would like to point out that this reaction process must be faster than the reductization process, such as fluorescence or heat, because at the S1 state, the fluorescence decay or thermal decay could happen, and if this oscillation energy is lost, and the chemical reaction does not happen. So this is the case. And here are some of the example. Not much no information, but so HI is this bond dissociated, or some of the complex molecules changed to so one of the ligand is released, something like that. So what happened in the case of the bimolecular reaction? Right. So in this case, the situation is a bit different. So you need to have one of the molecules necessary to react. So what happened here is that one of the A molecules light illuminated and excited, but if you need another molecule for reaction, it must encounter with B for reaction, right? So somehow for the reaction between two molecules, you need to have a collision of the A and B is necessary, right? And even if these two meet together, it's possible that the reaction process is can be slow, very slow. In this case, the reaction sometimes happen, but sometimes not. To understand this, some of the criteria, which is for this reaction, the Gibbs energy is the Gibbs energy difference is about 13 kilojoule per mole. In this case, it's the going down reaction, so the energy releasing in reaction, so its reaction is very fast enough. in this case, the diffusion to meet each other is the limiting reaction. So that's diffusion process. And this reaction is called a diffusion control reaction. And this situation is the same as any chemical reaction, actually. And then same for the photochemical reactions for involving the two multiple molecules. And in this case, the K, the reaction rate is actually limited by like this equation you could obtain from the kinetic analysis, but I don't go into detail about this here. But it's about 10 to the 10th molar per second. So you can see that if it's like concentration is like 0.1 molar, and then it's K equal 10 to the 9 kc round, meaning it's about 1 nanosecond order. So this is the fastest reaction in the diffusion controlled reaction. Of course, it depends on the concentration though. So with that, we studied various photochemical processes involved in the after the photo excitation.